Hello, my name is Aaryan Chatterjee, and this is my Oscillations Lab 4 in Physics 2211. Now, before we get directly into the lab, I think it's important to understand what the lab is precisely covering, which is energy. In real life, objects have many energies associated with them, like kinetic energy, spring potential energy, and gravitational energy. Now, in this lab, we will be focusing on analyzing the energies and motion of an object while attached to a spring. More specifically, this lab will be focused on analyzing and comparing the motion and energies of an oscillating mass attached to a vertically hanging spring, and there will be an observational and computational model that will try to represent the motion of the object. And later we will see that the models show that the energy principle is supported by the data results since the total change of energy is zero. And this can be seen by the graph on the right. However, before we get into lab specifics, it's important to understand some of the crucial physics principles and ideas utilized in the lab. Firstly, it's important that everyone understands Newton's second law, which says that net force equals mass times acceleration. And from this equation, we also get the velocity update formula, which will be how we define the velocity in the computational model. Additionally, we'll use a position update formula to find the positions in the computation model of the object in the lab. Furthermore, we need to know that the energy principle says that the change in total energy is zero if the work of the surroundings and the change in terminal energy is zero, which it is in this case. Finally, it is important to know that the total energy equals the summation of the kinetic energy, which is 1 half mv squared, the spring potential energy, which is 1 half ks squared, and the potential gravitational energy, which is mgy. Now we must cover some major assumptions in the experiment. So some of the major assumptions is that air resistance will not be included and there will be no other forces acting on the system. Additionally, it's also important to know what K, the spring constant, is, since the code needs it, and this picture shows you how we can find it by solving for K in the period oscillation equation. Since the tracker data tells us that the period oscillation will be 1.524 seconds, using that value and the previous equation, we can find that K is 6.83, which we'll use in our code later. Now, before we jump straight into the observational model, it's important that we discuss some experiment conditions. For instance, the system is the object attached to the spring, and the Earth, so there are no surroundings. The origin is where the spring is attached onto the wall, so the object starts below the origin in the negative y direction. The time period we will be analyzing the object's motion and energy will be from t equals 0 to t equals 9.402 seconds, and the object has an initial velocity of 0 at t equals 0 seconds. Finally, the frame rate is 10.5 FPS for the video, so through some estimating, I found delta t to be 0.005 seconds, which is a multiple of the frame rate and allows for the best results. So for the actual experiment, I used the provided video on Canvas to show the oscillating mass attached to a vertically hanging spring. And with this video, I inputted into Tracker, calibrated the video, and then plotted every individual point in the video to find the x and y components of the position of the mass. And this is a video after it's tracked by Tracker. Now, after that was tracked, it then outputted a table of position points, which I used to compare the code of the computational model to see how similar or different the results of both models. Moving on to the computational model, I first inputted the initial conditions, so I set the object's mass to 0.402 kg, I set the object's position to negative 0.094 meters in the x component and negative 0.665 meters in the y component, which I know from the tracker data. I then set the initial speed to 0 and delta t to 0.005 seconds. And then I set the spring constant to 6.83 and the relaxed length of the spring to 0.123, which were the values we found or were given from the video. I then found the length of the spring at the start of the video and the total difference between the relaxed length of the spring and the current length of the spring. Then in the loop, I found the initial kinetic energy, spring potential energy, gravitational potential energy, and the total energy of the system at the start of the video using the energy formulas that we know. Then in the loop, I found the forces acting on the object, which is a gravity and spring force. Then with the net force, I updated the velocity of the object using the velocity update formula, and then I also used the position update formula to update the position. After that, I found the change in all the energies at the end of the loop, graphed the energies and positions, and then incremented the time to continue evaluating the object's motion and energies at different times. After coding the computational model, when the code is run, the program outputs two graphs comparing the x and y positions of the object in the computation and the observation model, with the computational model being the blue line while the observation model is the red line. From the results, it can clearly be seen that the computational model is very similar to the observational model when it came to the x position of the object, which indicates the computational model is very effective in finding the x position of the object. Unfortunately, the computational model struggled a little bit more when finding the y component of the object since the program underestimated how far in the negative direction the object would go. Although the y graphs can be similar at some times, these results indicate that the computational model is less accurate when it comes to estimating the y component of the object. Additionally to the position graphs, the computational model outputs an energy graph showing the energy of the objects at all times. More specifically, this graph shows the change in kinetic energy, the spring potential, gravitational potential, and change in total energy of the objects at any given time, and claims that the total energy change is 0 at any time, which we will talk about more in the slides. Now, moving from our results, it's important to know that there could have been some track errors, like selecting different sizes of mass, and the lack of errors in our model could change the results a little bit. Now, moving on to the important question today, crucial to ask whether or not the energy principle is satisfied. We know that energy principle states that the change in energy equals the work done by a system by the surroundings and the change in thermal energy. If there are no surroundings in the scenario, the change in energy should be zero, and we can clearly see the model showed that the change in energy is zero, so the energy principle is satisfied. Moving on to that, we can see the period oscillation for the X and Y component are different. This difference to oscillation affects the spin constant, the spin conduction energy, and this difference can be explained to track errors or errors, and that's all from the presentation.